Okay, today we'll continue. So previously we covered the case one, where case one is the size eta. So basically, when we are interested in estimating eta for the model, right? Now we have a parametric model. Now we are more interested in general parameter psi, which is defined through an estimating equation. So in this case, so we want to still apply the imputation, right? So U hat is an estimating function on the complete response, and then we apply imputation from MLE. So let's think about using the MLE to generate the imputation, and then apply. So take the Monte Carlo mean, Monte Carlo sample mean. So we can write it this way. So M refers to the Monte Carlo sample size, and the second argument at head MLE means that it is generated from right. So it depends on the at head MLE in computing the Monte Carlo sample. So this is imputed estimating function, right? So and then we solve it for zero. Solve it for set it to zero to solve for eta. So that will be imputation estimator. So that and then question is how to find the influence function and how to compute the variance, all these kind of thing. And so that is the another paper by Biometrica, to say another Biometrica. Excuse me. And Robbins and Wang, so they showed that this result. So okay, your parameter of interest is to solve a solution to this equation on the complete response, and then now you have missing data, so you take the conditional expectation. So now here we just compute the so that is the m goes to infinity, right? So if an m goes to infinity, then this is just the conditional expectation. And then what is the asymptotic variance? So then this is the answer. Basically, we have a mean psi 0, so true mean, true parameter converted to parameter, and the variance has a sandwich form. So tau and omega. So omega is the core part reflecting the imputation variance. So let's briefly so we used an example to show this, but let me just make some comment on this result first. So okay, so actually this is 14. So to understand, well, actually no, for 15, sorry, 15 is correct. So to understand, so basically this is Taylor expansion, right? So this is the linearized variance, and then this is partial derivative. And so question is, how we can obtain this coefficient? And here's the idea. So first note that we can express this conditional expectation, and then whatever the linearization will be this form, because we will linearize with respect to right. So we remember, okay, so you had originally this is at the head, right? So we want to linearize with respect to eta, and then the limit. So if you write it as just this way, psi and eta head, okay, and then apply Taylor expansion. Then you will do something like this, right? Plus, so whatever, I mean, something like this. And then, but the point is that end of the day, this guy will be proportional to this guy. The score equation, score function that compute the, so because the solution to eta hat equal to 0 will be, right? So solution to this equation will be eta hat. So that means your the result of your Taylor linearization will be just the linear combination of the original function and the equation function, estimating function that computes the eta hat. And then kappa is a coefficient that characterize the linearization. So the question is how to determine kappa, and then the idea is to so this guy, if you view it as a function of kappa, I mean kappa and psi and eta, you, because we already view it as a linearization with respect to eta, if you take the further partial linearization, I mean, first take the partial with derivative to with respect to eta, it should be disappear, right? I mean, because it's already linearized. So that is the idea. So basically we can put this into here, right? Here, and then solve this equation that is actually the solution will be eta, I mean kappa star. So that is the idea that renders used. Okay, so that's just another way of understanding the linearization. But formally we should use joint equation. So here's the more formal way of thinking. So basically we have two unknown parameters, psi and eta. So that means we have two equations. Okay, one is the original equation, original estimating function, and the other one is the estimating function for eta. So you have basically joint estimating function equation. Okay, so basically, so you are interested in finding the linearization with a given eta hat, right? And then you should ask yourself, what determines eta hat, right? So that eta hat should be determined by some equation. So let's call that equation to eta u2 eta hat, right? I mean u2 eta equal to 0. So eta hat should, so I mean there must be an equation that determines the eta hat. So then, and which is actually the observed scope, observed scope function, right? So so then once you just write it as a joint estimating function, then you can do the Taylor expansion jointly, right? And that leads to, so this is actually lemma 4.1. So that this is just a multivariate version of the lemma 4.1, right? Because what is lemma 4.1? Lemma 4.1 is just what is the, right? So what is the property? So solution, something like that, right? So minus, okay. minus expectation of the inverse u hat zeta 0. So that this is actually lemma 4.1. Of course, this is approximation. And so we just have so this is single, right? Zeta, and now we have a two parameter. So this is zeta hat. And you have this. And then the partial derivative now is a matrix because you have two equation, two parameter, right? So it's a 2x2 type of matrix. So then basically B11, you can write it B11, B12, B21, B22. And then so row corresponds to equation and column correspond to parameter. So that you have something like this. Okay. And then first of all, you can see that this is 0. Okay. Because why? Because this one doesn't depend on psi. Right? So you have at least some 0. And this one is 1. This is actually scope function, partial derivative of the scope function expectation. So which is the information, right? So that is information, obvious, and minus, I guess, right? So that is this one. Okay, so we cover this. And this is also easy. This is basically you are just computing the partial derivative with respect to psi, which is this one, right? And then take the expectation. So that's basically the same, right? Same so that doesn't really change anything. I mean, because you have also U1 itself is a position expectation, but for the first component, it's just doesn't really change. What is more tricky is this one. When you differentiate with respect to the second component, it's a little bit more tricky than the first, right? Then taking the partial derivative. So this is the main challenge, main hurdle, I guess. And then, but we already covered this topic before. So basically, so we are interested in computing eta, U bar, psi, and eta. So that is U psi given data and eta, right? So that is psi. So, and then F y miss given y observed eta d y miss, something like that. So then this guy can go inside here and then apply to the density function that actually becomes a scope function corresponding to the density, which is the S miss, right? So S miss eta and then density, right? So that is actually expectation of the U psi S miss. By the way, you have everything actually So that has this one. Conditional on data. And then you take the expectation. You take the expectation on this one, then you have a expectation on this conditional expectation, which is. So that take care of the final hurdle. Why? Which line?
So, in terms of eta naught, why eta naught?
B on two, B on two, B on,
B1,
B12.
B12, okay.
then beta naught.
So,
It's
Eta, psi, eta naught, right? So this is, so, when we say,
yeah. Okay.
so here, everything is evaluated at, so this is actually evaluated at the, right? Fix the value, I mean, which is null, eta null, and so, yeah. Okay.
Okay, I have a, so if the psi and right are the function of eta. Just say because eta is the parameters in the model. If the parameters we are interested can be written as a function of the parameters eta, so we can plug in, right, eta half to estimate the psi, right? So in that case, which method is better? Is this one more efficient than the plugging?
So actually what you're saying, if eta is, I mean, if psi is actually eta, right? I mean,
If psi is a function
of eta, then I think the theory here is not really applicable, right? I mean, here the Taylor expansion. So this kind of Taylor expansion already assume that they are different coordinate system, right? So you cannot really, so how can we, so this kind of expression already assume that you have a different coordinate system as a parameter.
Okay, but in the model, eta are all the parameters, right? Eta are all the parameters,
Okay.
right? So
Eta is the see, okay, you are actually saying that eta is actually function, I mean psi is a function of eta.
right, because eta are all the parameters in your
Okay,
model,
right,
So-
right, some sense, right.
So anything that you are interested in must be some function of eta.
I think in that case, two methods should be the same, equivalent, right?
Okay.
Yeah, that's a really good point. I think this, yeah, that's the point. So you're right. I mean, because psi is a solution to the given estimating equation, which actually depends on the parameter, I mean, model parameter.
Right.
So we don't know the form. You may not know the form explicitly, but so then your question is, okay, I see your point. So yeah, actually, that is actually, so you can suppose, right? Two choices. One is you compute the array and plug into this function to compute psi hat. So that is the actually MLE for psi. Okay. Otherwise, here this is not really MLE. This is more like a method of moment type estimator. So that actually applies to some comment that I like to make. So suppose psi is a proportion of y less than 1. Okay. So then you can actually, and y is normal. So for example, 1 and then f y theta, right? So here, this psi is this one. So it's like this one. It is actually a function of theta. And so you have actually two way of computing psi. One is the MLE, right? You just so psi hat MLE is actually computing theta hat MLE dy, right? So that's one way. The other one is actually solve method of moment is method of MOM estimator is a solution to right. You may use this one too. So you can just method of moment estimator is just a sample mean of the indicator for this event, and then this is more efficient, right? Of course, the first MLE is more efficient than the method of moment estimator, but method of moment estimator actually does not use the normal assumption, so it's more robust. So if the model, I mean, normality assumption fails, still this is unbiased, but this is not. So there's actually some kind of a trade-off. You have a bias and variance type trade-off. So yeah. Okay. So this theory actually applies to the second one, some sense, because we have an estimating function and then do this. This one is so for this kind of estimator, you just compute the set type MLE and then plug in, right? So that applies the first theorem. Okay, it's very good. Okay, so this is about section 4.2, and now I'm going to move on to section 3, 4.3. Okay, so actually, you probably attended a seminar yesterday, and that actually quite similar to what we are. So I'm going to explain a little bit on what the speaker did yesterday and make some connection. So the you didn't attend? Okay, try to attend. I mean, especially when you have once you learn missing data, many research seminar will be quite related nowadays, especially the causal inference. Yesterday is really directly related. Anyway, so remember, we have a missing data, and then yeah. So you guys get it, right? That is right. Okay. So this is a regression imputation, right? Originally, this is actually 1 over n, I equal to 1 to n, delta I yi plus 1 minus delta I yi hat, where yi hat is beta 0 hat plus beta 1 hat xi. But this is equivalent to this because you have a property of the residual. So and also last class we covered this, right? We covered this linearization. So we actually use some linearization to explicitly derive the influence function. Okay, so you can check the previous slide. Okay, so I'm not going to derive it again. I will just start from here. Okay, now, so now question is, so what, right? I mean, so what? So now, okay, we can accept this. Then what is the next step? If you are going to compute the variance, estimate the variance of the regression imputation estimator. So that is the point. So now here, let's first write it as a dxi yi delta I, right? This is function of xi, yi, delta I, and parameter, which is beta and kappa. So we can write it this way. And then notice that they are IID. Why? Because you have a xi, the assumption is this vector itself is IID vector, right? This vector itself is IID vector. So any function of the vector should be IID. Any function of the vector should be IID. So this function itself is a scalar function, right? Scalar function. But because the original vector itself is IID, then we can guarantee to assume that, guarantee to believe that this di, this function will be IID. So the idea is, so now for variance estimation of this regression imputation estimator, because of the equivalence, right? So the asymptotic equivalence here says that the regression imputation estimator is asymptotically equivalent to the sample mean of the DIs. So now let's try. So instead of computing the variance of this guy directly, let's try to compute the variance of the sample mean of DI. So that is the basic idea. Okay. So now suppose, okay, so then in this, so let's do the mental exercise. Suppose you observe DI. So DI is just another random variable. Then it's very easy because it's just computing the sample mean of the DIs, right? So we are interested in computing the D bar, variance of D bar, which is just this guy, right? If you observe DI. So if you observe DI, this should be your variance estimator. But the problem is that DI is a function of unknown parameter. So the form of the functional form itself is known, right? The form is known, but the parameter in the function is unknown. So then we have to plug in, right? So you need to plug in. So we have two unknown parameters. One is beta, but beta we know how to estimate it, right? So beta is this parameter. Already we know we have an estimator. So that's no problem. What about kappa? So let's go back to what is the definition of kappa. Kappa 1 and kappa 2 is essentially a solution to some sort of equation, right? So that, and then this is basically moment, right? Moment. So that should be easy to compute, right? Easy to estimate from the sample, which is this one.
So this is why kappa is defined like this.
Huh?
Why kappa is defined like this, kappa 1 and kappa 2.
Kappa 1, kappa 2?
Yeah. Why it is only data?
Okay.
So why kappa 1 and kappa 2 is defined like this?
Why you get this one?
Yeah.
That we covered in the previous lecture. Okay. Yeah, sorry, you have to probably remember a lot of things. So I can show you some evidence. Actually, sorry, should be chapter 4.1, right? This one, right? So yeah. Okay, yeah. 2 weeks, I mean, it's already more than a week ago, so it's fully understandable to forget. So actually it's 4.1. Okay, so we have this one. Now, so that means you have a variance estimation formula. Right, using all this, you have variance formula. So that's a little bit tedious. I mean, how you derive all these. It's very labor intensive. Okay. Go ahead.
So these are like pretty common in sample service. So is that why the speaker yesterday was talking about so for asymptotic theories for these kind of experiments? Is it why he was talking about results from sample service?
This one has nothing to do with sampling, right?
No, but we see these kind of estimators in sample service.
You mean
Yeah,
This one?
the estimate of the variance. Yeah.
well, this is IID sample mean.
Yeah, okay.
So well, I don't know. I mean, this is here. You don't have to have any survey sampling idea here at all. It's just IID. So this is the sample mean. So the variance estimate should be 1 over n s squared, right? Which is this. So yeah. Well, what I like to make the connection is start now from now with the seminar yesterday. So the seminar speaker yesterday, seems to be very excited about his finding, and that is not really new. Yeah, I mean, it must be new to him, but not really new to the community, statistical community. So let me explain why. So he kind of argued that the regression imputation estimator here, so regression prediction is a weighted form like this. And actually that is not really new. I can show you that this is actually, so first of all, beta 0 is a linear function of y. That you can see, right? So end of the day, okay, how we can compute beta hat? Beta hat is x prime. So we have a delta. So xn prime delta n, xn inverse xn prime delta n y. Can you understand this notation? So we can think of linear model, right? So xn, x1, x2, xn. Right? You can make a n by p matrix, generally speaking, and then delta n is a diagonal matrix of delta 1 to delta n, and yn is just the y1 to yn. Okay. So if you do that, beta hat here, right, it's just this one.
Simply use the complete data for.
It's just that it's discrimination, right?
Please complete then.
With the complete data, right? So that's why I put a delta n here, because we are using only delta equal 1 cases. So the point is that, my point is that this beta hat is a linear in y, right? It's a linear function. So end of the day, you have a yi. So y1 to in, and then you have just some weight. So this is end of the day, your estimator here will be just the weighted sum of the weighted mean of the yi. And turns out that your weight is very simple. It's a very simple expression. Why? Well, so let me continue. So theta hat I regression. So regression imputation estimator. Prime x I prime beta hat, right? So if you use vector notation, that is actually 1 over n. Let's use all vector notation. So 1 xn prime delta n xn inverse xn prime delta n y. Okay. So what I write is, so we know this is the regression imputation estimator, which using the vector notation, matrix notation, this is your estimator end of the day. And what we like to express it here is that this is what? 1 over n, just the 1 prime. No, not 1 prime. We have a w n prime delta n yn. That's it. So now question is, what is wn? So wn prime is exactly equal to this. Right? And then that's very interesting because why? Because the expression here, so this one actually, if you write it xn prime delta n xn times kappa equal, so another way, sorry, maybe I should write it directly. Kappa, vector kappa is xn prime delta n xn inverse xn prime 1. So we can actually use this. So remember this one is actually probably some of you probably know notice that. So this guy here is already kappa. Right? So you get so basically my point is so okay, let's go back 1 prime. Okay, actually kappa prime, that's confusing. Yeah, so kappa prime xn prime, right? Yeah, so that actually shows, so so as a vector, this is equal to this is actually this one.
Kappa prime is
Huh?
the weight. Kappa prime is
So weight, yeah, so the weight, so basically you have this algebraic equivalence, right? And then you can, end of the day, you can write it weighted right? Weighted weighted yi, and the weight actually is a linear with the coefficient kappa 1, kappa 2 that we. Okay. So, and then, yeah.
Is there any like implication for such rule?
Huh?
Is there any implication?
Yeah, I'm explaining. So several implications. So one thing actually notice that you can actually, so this one looks familiar, and that is actually here, right? So if you have a plug in here, this is W. So that means you end up writing the DI hat will be of this form. Okay. So that means your variance for variance estimation, you need to compute the DI hat, right? So you need to compute the DI hat, apply some variance estimation formula. And DI hat is prediction plus. So remember, if W equal to 1, suppose if W equal to 1, then it is just the imputation, imputed value, right? If W equal to 1, then you have a delta I yi plus 1 minus delta I yi hat, which is basically imputed value. And if you just use imputed value, you know it's underestimate the variance. So you need to inflate, and the amount of inflation turns out to be exactly equal to this W that you obtain after all this linearized, algebraic expression.
Can you repeat the underestimate argument?
Huh?
Can you repeat the underestimating argument you just said?
So if W equal to 1, then it underestimate. Because you treat imputed data as if the real data is applied. But the missing data increase the variance. Okay. So so variance estimator naively applied by imputed data. So okay. Imputation, first of all, imputation increase the variance. Why? Because you have a missing data in the beginning. So you cannot really, so you pay the price, right? You have a missing data. So that means you are actually using less information than original sample. So so the variance increase. Okay. And then naive variance estimator doesn't really play. So well, let's really simple. Suppose you have R, missing complete random. So this is the variance, right? And this is missing data. You have without missing data you have. So which one is bigger? This is bigger. Right? So N is 100, R is 50. Okay, then you basically double, right? Your variance increase double. So anyway, so that turns out that when you first compute this linearization, right? When you first compute the linearization all the way, you have to do a very tedious linearization, right? I mean, you need to compute all this, and but so even this one is not really easy. You have to do all the hard work, right? I mean, so very labor intensive algebra. But end of the day, your formula is very simple. Your formula, all you have to do is figure out what is the weight applied to the final estimator, applied to yi, and then use the weight applied to your residue. So that is the one formula. Actually, this is published in my first paper. My first paper is about this magic formula. I should call it Kim's formula, but I didn't. so,
So here, the WI, do we have a room for WI?
I'm sorry.
Do we have a room for WI? Is the weight always larger than one or?
Well, this is about linear regression. Linear regression there. So then WI is what you obtain. All this.
Right. Right, I mean, we cannot show, for example, W1 is always not larger than one or something like that.
No. Actually, you can see that this is actually linear, right? So linear, so if you, for some extreme X values, you can even take the negative value. That is the limitation of the regression rating. So yeah, there's a way to fix it, but that is the one important point. So actually, let me move on. Okay.
So we are using the interior value only delta equals to 0.
Right.
But if delta is 0, we simply just have d hat equals to y. So how does the W work?
But this is for a formula for variance estimation. So this is for only for work for variance estimation. Okay. For point estimation, you should put W equal to 1.
But if delta is 0, if we do not observe.
Right. So delta is 0, you don't observe this one. But you do observe X so that you can compute y I had.
So and we use y I hat to estimate the variance, or because we plot.
We use vi hat to compute estimate the variance.
Yeah. So if delta equals to 1, we observe y I.
Well, I don't. Okay. Well. Delta equal to 0, we have this one. Delta equal to 1, we have something this.
So for delta is 0, there is no information that we can adjust it. We can only adjust it when we observe the data. So that's why the weight adjustment is applied after observing.
Right. The weight of adjustment is only applied to the observed data, delta equal to 1 case. So yeah, so of course, this weight is greater than 1 on average, but not necessarily for particular unit. Actually, this is very important concept. This weight is called regression weight, and this regression weight satisfies this. Okay, so that means what? The regression weight. So if you multiply both sides divided by n, basically the regression weight applied to intercept. So why this is important? First of all, suppose your YR is exactly equal to a linear function of xi. Suppose you have this exact linear relationship, then what happened? That means your weighted estimator is actually equal to okay, and so you have a something times 1 plus beta 1 times x bar. So that means u is exactly equal to 1 over x. No loss of information. You fully recover information if there's a perfect linear relationship between y and x. Which makes sense, right? I mean, you want to use regression relationship to recover information, but suppose that regression relationship turns out to be perfect, then you don't lose anything. So that's one implication. So that this property is called calibration equation in survey sample. Calibration weighting and calibration. So basically we calibrate, right? The weight. So we do some adjustment. So originally, right? Okay, if there's no adjustment, then what would be the weight? The weight will be, if there's no adjustment, then the weight is just 1 over R or something, right? We don't do anything, but equal. But we intentionally change it a little bit to satisfy this. And turns out that you can actually, by the way, let me first show why these words, right? I have, so okay. So let's discuss why this equality holds. So okay. So maybe we can write it W, so left hand side equal to W n prime delta n and xn. Okay. And so that is actually we have already, so that is 1 prime xn prime delta n xn inverse xn prime. Okay. So what I did is just use the definition. So that is the left hand side, which is this one. And so now you can see that cancellation, right? So you can see there's a cancellation. And then you have this one. So that is, which is right hand side. Oops. Okay. That is, so I now prove this. Okay. So that is, so here's a, we can write regression is, first of all, we can understand regression is imputation as just a prediction, right? So prediction, but because the prediction is a linear in Y, so at the end of the day, we can write it as a weighted average, right, of the observation. And so then we are curious of what is this weight is doing, right? What kind of property this weight satisfies? Turns out that this weight satisfies the calibration equation. And so another way of understanding is something like this. Suppose you have a original data is something like this, okay? So suppose this is your original data, linear regression. And now we have a missing. So we have suppose we have a observation. So we have observation mainly smaller So we have a higher probability of response in the smaller x values. Okay. And so the relationship between y and x doesn't really change. This thing stays this thing at random, but we know. So mean of x here is x bar r. Okay, while the mean of the x in the original data is here, x bar n. Okay. So then x bar r, you have a y bar r, right? But because of the property of the residual, so you use the sample only to fit a linear regression, and so you know you have a observable sample mean of x and sample mean of y, everything. But now we already know that we have a we over select, right? So the small values over represent, because we know that x bar, we know this one. Then my sample, my responder turns out to select the small x values. So then how should we utilize this information, right? How to utilize this information? Well, maybe one way is to predict. Right? Predict at x bar n. So that is my y bar regression. Okay. So here so this is one way. Another way is when we can actually use this one, and construct a weight. So we put higher weight to bigger axis. Okay, and do okay. So that is basically the idea of, anyway, that is the idea behind regression weighting. And so that's what the seminar speaker is very excited about yesterday. Okay. So survey sampling and missing data developed much before than causal inferences. So we have then we have a good chance to have some more advancement in the literature. So anyway, okay. So now turns out that this particular way can have a very interesting optimization interpretation. So we minimize this guy subject to the calibration, or this one is actually minimizing this guy is actually equivalent to minimizing minimizing this guy is actually subject to the constraint here is equal to minimizing this guy subject to the same constraint. Because if you expand it, then quadratic term and then linear term, right? The linear term actually is part of the constraint. So that is actually that doesn't matter. So my point is, okay, delta I wi square. So minus 2c delta I wi, right? Plus c whatever constant. So point is that this guy is actually fixed in the constraint. So that means minimize this one and minimize this one is the same thing. But once you write this way, you have some interpretation of the distance, right? You have suppose you have c is 1 over r, right? Or 1, I mean 1. So you want to minimize the distance. So you want to minimize the distance subject to calibration constraint, something like that. So that's interesting interpretation. So now let's move on. So we use how to solve this kind of problem. We use Lagrange multiplier, right? So let's use vector. So that is our objective function. So x is and so go to 0 implies actually we should better to 1/2 here, so that you have a wi plus lambda prime xi to 0. So whatever the solution is linear wi. The solution to this problem is linear in xi. So which actually means that, but we already know that lambda hat equal to kappa minus kappa satisfies right? We know that already. So that this is the solution, actually.
So if it's the condition subject to 4, are you fixing the whole summation of delta I wi 1 xi the whole way, both of the components?
So okay, everything is fixed. The only thing unknown is wi. Okay.
So I'm confused because at the right side you wrote summation of delta I wi fixed, but in the Lagrange multiplier you took summation of delta I wi xi. So what is the constant? That's why.
So C is this. This is C. This has nothing to do with the W. Okay. So well, this is just for convenience. We don't have to write a C. You can just write it this guy. No problem.
The first xi is the scalar, the second xi is the.
Oh, yes. So that's actually one and okay.
Okay, thank you. So
The objective is the variance, right? The variance.
exactly right. Right.
The variance.
Exactly. That's a really good point. So see, if you that is actually I kind of wonder whether I should say that or not, but since you know, so okay. So what is this exactly, right? How to understand this? Well, we can write it. Maybe you can write it this way: beta 0 plus beta 1 xi plus ei. Okay. So we can write it, right? I mean, what is this? Oh, sorry, I have a delta I. So delta I, right? So summation wi, delta I, wi, yi. Summation, if you do that, nice thing is because of the 4, you already have this one. And then what you end up having what you left with is delta I, wi, ei. So this guy is actually variance of this one. So you want to, so what is the variance of this guy? Where one way is to, because we know this is the best, right? So, or we can maybe minimize this one subject to this constraint. That achieves the best. Okay. Actually, I didn't prepare this remark, but the seminar yesterday motivated me to to add this one just to make the connection.
So another related question is why we do not like the negative way?
Huh?
Why we do not like the negative way? Because that is basically the motivation for the speaker yesterday to write several papers. They put a constraint on the way to be non-negative and propose some new. Yeah, so why we do not want negative?
Well, so if you negative weight, I mean, actually, this kind of problem has been this investigated long time ago, like so 1978 in survey sampling, Huang and Fuller. So in the survey, so you're right. I mean, if we have only single Y, then actually we allowing for negative weight is actually okay. But in sampling, we have a multiple Y's and single W can be applied to several different. So having negative weight is not acceptable. Because survey we usually pay money to collect information, and then you pay, say, so I collect single information from one person by paying $100. So I pay you $100 and get all the survey, and then after that in the analysis I put zero weight. What's the point, right? Suppose I put zero weight. Why should I pay? Zero weight is actually giving zero weight is deleting, right? And then why should I collect all Y information and pay money? End of the day, when I put zero weight, right? That's nonsense. So that means, I mean, and also, in survey sampling, every element is a part of the population. So at least I represent myself in the population, right? So putting zero weight doesn't make sense. And I should at least represent 1 over capital N, right? I mean, so, okay, point where this is a little bit different story, but suppose the population is 1,000 and sample is 10. Then on average, each person is supposed to represent 100 people, right? On average. And but for some reason for this calibration, suppose if one particular element end up giving zero weight, that's not really good, because even if that value is extreme, it actually is a part of the population. That's a bit different story. Let's move on. Well, so there's a lot of actually literature on how to modify the weight to avoid extreme values of the weight, final weight. That's quite well studied in the literature. Well, okay. Oh, I already. So let's move on. So impedance estimator can be written as. So that's remark. So, and then we have actually two choices. One is the deterministic imputation. The other one is the stochastic imputation. So deterministic imputation, we just impute, best predictor, no error. So here the point is that the imputation estimator depends on unknown parameter, estimated parameter, which we can view as a nuisance parameter, right? So how to reflect the uncertainty in the nuisance parameter is the key issue, and that issue needs to use the linearization. And so idea is we want to linearize to get di, and then idea is we once you figure out this di, then we can plug in the parameter to obtain di hat and obtain the variance estimator. So that is basically the idea. Stochastic imputation, we have additional term. So the idea is the stochastic is always increase the variance. And you may wonder why use stochastic imputation at all, right? Why you increase the variance? What's the benefit of doing deterministic imputation? I mean, using stochastic imputation. So that's the actually so if you do deterministic imputation, so one drawback of the deterministic imputation is that deterministic is that you under represent the true variability. What does that mean? The data has certain variability, right? I mean, and then if you use best predictor, you are kind of doing smoothing. You are doing over smoothing. And so end of the day, your imputed data has a less variability in the data file, which may be okay for estimating the mean, but not okay for estimating the proportion, for example. So suppose, for example, this is the original variability, okay? And you are interested in computing, say, this proportion, okay? So this is your, the area here is your parameter, for example. But if you do mean imputation in the extreme case, so that means you have a missingness everywhere, okay? And then the missing and the missing values are all imputed by median, for example. Then what? Then you have a peak after imputation. You have a peak, right, in the center, which actually gives a bias estimate of this proportion, right? So that, and also bias estimate so you underestimate the proportion of the extreme values. So that actually can matter in some cases. So then idea is to add noise intentionally to reflect the variability of the original data. So that is the idea behind stochastic imputation. Okay. So then you basically idea is you separate out, and so this is the additional variability, and then you need to figure out what is the variance. This is kind of bootstrap. So this part, computing this part is not really difficult. But the point is, you sacrifice efficiency, right, in stochastic imputation to achieve other robustness in parameter estimation. I think that's all for today. So I will continue this Thursday.